Welcome back. So in the previous video we arrived at these two equations, two expressions that define the Fourier transform here. And we have equation 1 wherein you are actually transforming your time domain signal, that is this x of t, to frequency domain signal x of omega using this integral. And then we have the second equation which helps us to get back our signal x of t from the frequency domain representation, right? So my forward equation, your transform equation, it gives me x of omega from x of t, fine. And then my second equation gives me x of t back from x of omega. So there's a, it's a kind of a bilateral thing. You're transforming from time domain to frequency domain, then you also need some way of getting your signal back into time domain from the frequency domain. And you'll see that this will be a common trend. जो भी transforms हम पढ़ेंगे, we will do Laplace transform, we will do Z transform, and each of these transforms are defined by a pair of equations. The normal transform, which we sometimes call the forward equation, which helps you to transform from time domain to frequency related domain, and the inverse equation, which will help us to get backward signal from the frequency domain to the time domain, right? Now you may ask, why do we need this transformation? And you will come to know, you see there are some operations, there is some analysis that is better suited for frequency domain. When you go to your next class, you will study communication there. And there is one thing we are really interested in communication, is the power content that each frequency contains. We deal with signals in communication, so you have a kind of a complex signal which has a lot of frequencies, fine. And जैसे आपका audio signal है, it has a range of frequencies, and more often than not you're interested in that the range of frequencies, the frequencies that exist in this signal, what is the power content of each of these frequencies, right? So that kind of analysis becomes very complicated if you perform it in the time domain. So what we do, we transform from time domain to frequency domain, do the analysis in the frequency domain like this power spectrum analysis, then come back to the time domain, okay? And in many cases you'll find that transformation from time domain to frequency domain, it simplifies your operations. So we'll be doing one such operation. We have done convolution in second chapter, and you know convolution in general is a complex operation if performed in time domain. But you will see that when we will apply these transforms, the convolution operation is simplified, right? So there is a general trend that you analyze in frequency domain. Most of the times you analyze your signals, your systems that they represent in frequency domain, do the analysis, and then design and implementation is always carried out in time domain. Anyways, we have this pair of expression. But the thing is that your x of t, that this forward integral, this getting frequency domain representation from time domain representation. Now to enable this, there are some conditions that x of t must satisfy. These are sufficient conditions, they're not necessary conditions. It means that even there are signals which may not satisfy one of these conditions, but you will be able to find their transform, right? So we say that these are sufficient conditions but not necessary conditions, right? So if a signal x of t adheres, follows these conditions, then definitely you will be able to find the Fourier transform of such a signal. In case a signal it's not following one or couple of these properties, then you may find the Fourier transform, you may not find the Fourier transform. So we say these are sufficient conditions but not necessary conditions. And as far as Fourier transform is concerned, we basically have three such conditions which we collectively call as Dirichlet conditions, fine. And these are the sufficient conditions, means if a signal satisfies these conditions, you will definitely find a Fourier transform, but not the necessary conditions. We have three such conditions. We'll start with this one. Actually, this is not a part of your course, but sometimes they ask these things in interviews, in your GATE exams. Okay, so we start with this, that x of t, it should have a finite number of maxima and minima within any finite interval, right? So it means that if you have a signal, obviously we're talking about Fourier transform, so it's going to be a non-periodic signal. So you can take any signal, something like this, where period is not defined, something like this. And if you choose a finite interval, say if I choose an interval from here, let's say to here, and within this interval it should have a finite number of maximas and minima. So if you analyze, you have one maxima here, two maxima here, so you have two maximas, which is a finite number. Similarly, as for minimas are concerned, one minima, two minima, third is here, so you have three minima. So these maximas and minimas for any finite interval, they should be finite in number. This is one of the conditions, one of the Dirichlet conditions. Then second is x of t should have a finite number of discontinuities within any finite interval. Again, we take in haphazard form, say we have a waveform like this. Right? And again, you can choose an arbitrary interval, say from here to say here. Now, if you look at the discontinuities, we start from here. This is the first discontinuity, then here another discontinuity, then another discontinuity, another 4, 5, 6. So these discontinuities should be finite, fine. And to add to it, and finite, and each of these discontinuities should be finite. The number of these discontinuities should be finite. Say for example 7 यहाँ पे आ गई, and income value, for example, this continuity has a value of 1, which is finite. Let's suppose this discontinuity has a value of 2. Say this has 0.5. So these are all finite values, right? So first thing, that it should have finite number of maxima and minima within any finite interval. Second thing, that the signal x of t should have a finite number of discontinuities within any finite interval. And the value at these discontinuities, it should also be finite. Then there's a third one, that x of t should be absolutely integrable, which means if you take the integral of x of t over the limit minus infinity to plus infinity, the value should be a finite quantity. And together these three conditions, they are known as Dirichlet conditions, and these are sufficient conditions for the convergence of x of omega. Means if your signal x of t satisfies these three conditions, you will find the Fourier transform, and that transform will be a finite thing. It won't be infinite, it won't be not defined, it will be defined. But please remember, these are sufficient. There are cases wherein the signals, they may not satisfy one or two properties. For example, this x of this absolutely integrable, but we are able to find their what you call Fourier transform. So these are sufficient but not necessary condition. So this was in relation to this, the Fourier transform, that these three conditions, they have some significance. So next we'll take some examples, some simple examples, and we'll try to find out the Fourier transform of these signals. Let's take the first one, where x of t is an exponential signal modulated by a unit step function u of t, and a is greater than 0. Fine. So if you find the Fourier transform, we have this equation, x of omega is equal to minus infinity to plus infinity, like this. But since this signal is modulated by unit step function, it means that it will only be defined for the positive values of time, that is 0 to infinity. From minus infinity to 0, u of t is 0, so we won't be including that as a part of the integral. Then we have the signal e raised power a minus at, फिर जो transform का e raised power minus j omega t dt. Then you can just simplify it. It is 0 to infinity e raised power minus a plus j omega t d of t. Right? And you can solve the integral. You will have it will be like this, and this will stay as it is, a plus j omega t between the limits 0 to infinity. Then you may proceed to limits, so it will be minus 1 divided by a plus j omega. The upper limit will render it e raised power minus infinity, and for the what you call, okay, this will be, okay, this is the common thing, so it will be like this. Right, so this will be e raised power minus infinity minus e raised power 0. So which will be 1 divided by a plus j omega, as this will be 0 minus 1. Accordingly, it will be like this. Here obviously a is greater than 0. So this is the Fourier transform of this signal, exponential signal, which is modulated by unit step function. Then let's take another one wherein we'll try to find out the Fourier transform of a unit step, this impulse signal. Which maybe we can use the same integral x of omega, but the thing is that delta t is defined only for one instant of time. Fine. So we had done few properties of the impulse signal in the continuous time domain. So you know this is basically the value of this function at t is equivalent to 0, which obviously is e raised power 0, which is equivalent to 1. Then let's have another one wherein I have a rectangular pulse signal. So it is a rectangular pulse signal, and we want to find its Fourier transform. So it's a pulse signal of this type, x of t. It has a value of 1 for t less than t1, and outside this it is 0. Okay, so if you want to plot it, simple subplot hoga, because magnitude is involved, so it is on the either side of 0.0. So this is 0. It extends from minus t1 to plus t1, and we want to find it. Again, it's a non-periodic signal, because it's not repeating itself. So again, same thing, just apply the formula. It may be slightly involved here. So x of omega, it is equal to minus infinity to plus infinity x of t e raised power minus j omega t d of t. Fine, but the signal is defined only for the period minus t1 to plus t1, so we'll change the limits, and it has a value of unity within this range, so this will be our integral. Then you can solve it. I am sure क्या ये आप solve कर पाएंगे. So it will be like this from the limits minus t1 to t1. Then as you proceed to limits, it will be 1 by j omega e raised power minus j omega t1, the upper limit, minus e raised power j omega t1, the lower limit. Then you can change the order so that we are able to express it as a sine or a cosine function. J omega t1 minus e raised power minus j omega t1, and this is basically the Euler's expression. You can always express it as 2 times 1 upon omega, just to get it in that form, e raised power j omega t1 minus e raised power minus j omega t1 to j, let me just check, omega 2 into, okay, and that it will be equal to 2 times sine omega t1 by omega. It's kind of a sinc function, and I'm sure कि आपने graphically ये देखा होगा. There is a function like this which continuously decreases like this. Right, so this is my x of omega. So you can say in time domain, this is your rectangular pulse, the representation of rectangular pulse in time domain. But in frequency domain, that is when we plot it against omega, this is its equivalent representation. ये आप अक्सर देखेंगे in your communications course, we do a lot, we use this a lot in our communication. So this is a time domain representation, this is the frequency domain representation. Yeah, and this is something to do with that power spectrum. You see that अगर इस representation में you try to find out what are the individual frequency components in this signal, it will be slightly different. You can do it, मैं ये नहीं कह रहा हूँ it is not possible. You can take the incremental approach and can do it, but it will be very complex. Frequency domain में you see this is the omega axis, these are the frequency points. हर किसी frequency पे there is some amplitude, and that will give you an idea about the intensity and the power content of that particular spectral component. Okay? So these are few examples. In the next video we'll try to see into some properties of the Fourier transform.